Lab 1, Constant Velocity. The purpose of our lab is to show that Newton's laws accurately predict motion by modeling the anticipated motion of our system in GlowScript and comparing it to our actual results. We will also learn where certain problems can cause our results to vary. We will observe an object rolling with a relatively low coefficient of friction, which will serve to somewhat accurately depict Newton's second law of motion. The results of our code and tracker calculations were very similar, proving Newton's second law was in action, but seeing as we did not perform our experiment in a perfectly closed surrounding, the results did vary slightly. The main idea of our experiment is that Newton's second law is applicable in not just our case, but universally. We know that force equals mass times acceleration, and we can conclude that with a net zero force acting upon our system will also experience zero acceleration or uniform motion. The mass for our system is not entirely important, as with our acceleration being zero, we can conclude that force will also be net zero. And no matter what our mass is, it's going to be multiplied by one of those two variables, which is zero. The goal of the lab is to connect real motion to physics principles, so the best model to use is Newton's second law, which tells us how force changes acceleration. Because our object is moving at a constant velocity, it must have zero acceleration. Before we get into the experiment, we have our system, which was the expo marker that was rolled, the surrounding, which was everything else, the table, gravity, drag, but we won't factor in these other forces as they would overcomplicate things. And our initial conditions, although a force was applied to the marker to get it moving, we'll set that aside and envision that our marker was already moving at a constant velocity starting at t equals 0.2 seconds. This goes for both the tracker and our code. In our experiment, we rolled a marker across the table and set our initial time to 0.2 seconds to simulate constant velocity with no force acting upon it. We then used Tracker to calculate its position relative to time and created both a table and a graph representing our displacement over time. With that, we were able to conclude that the force acting upon our marker was negligible and that our velocity was near constant, proving Newton's second remained true. Looking at our code, it was relatively simple, only requiring a few variables to get working. We also utilized some other lines of code to make our information illustrated as a ball moving across a straight path at a constant velocity, just as our marker did. With the output of our code, we found Newton's second law to be perfectly true, as the position update formula allows us to see the velocity of our marker was unchanged as time passed on, showing that there was no force acting on the system. Over the course of time in our experiment, we saw the velocity did change, pointing towards the fact that there were forces not taken into account acting on our system, along with inaccurate tracking. Over the iterations in our code, however, we saw a perfect representation of Newton's second law, where net force equaled zero and acceleration equals zero. With this being said, the change in velocity was very minor, and seeing as our experiment was not able to be performed with extreme precision, we can still infer that Newton's second was at play. The most obvious source of error in our experiment is the fact that our tracking was not extremely accurate, and we also didn't factor in gravity, drag, or the friction between the marker and the table, which caused the marker to decelerate. Overall, I think the experiment was a success as it allowed us to physically visualize Newton's second law, and seeing as how we didn't have the resources to perfect our experiment, they surprisingly came out pretty accurate. In order to have our experiment and code output be more perfectly equal, there are some things we could have done to improve the results, including using better tracking software and maybe more input into our code to more accurately reflect what was happening in real life. If we flip the x-axis, since we rolled our marker from right to left, our displacement would go from negative to positive, and our velocity would remain largely constant, although its direction would be opposed to the original experiment. So the only thing that would change would be the direction, but the magnitude would remain the same. In our code, we set our force acting upon the system equal to zero to perfectly model uniform motion over time, but in actuality there were forces at play that were not equal to zero. Gravity and the normal force were net zero, but friction and drag were also acting on our system, causing deceleration over time, which our model in GlowScript did not show. Overall, I think the experiment highlighted a few very important physics principles and introduced us to coding as a means to verify the accuracy of our experiment. I'm pleasantly surprised with the magnitude of accuracy we were able to get in the classroom, but would love to see if it could be improved. I'd like to revisit this experiment over the summer and see how I can improve my code to more accurately model the actual data collected from my experiment, as well as see if I can calculate the other forces acting on our system that caused it to experience non-uniform motion.